Hello, everyone. Yeah, my name is Pascal Brückner. I'm from TU NHR. It's the security team at TU Dresden. And you just heard a lot of good advice and a lot of best practices on how to configure HPC systems and what to keep in mind when running these. But I will now show you an example of what can happen if you don't follow that advice, or if some of these things aren't followed correctly. This is a real incident which happened last year. It originally started in the end of 2019, but people became aware of the attacks in 2020. And then a lot of news outlets titled "Supercomputers are offline across Europe." Here are two examples for that. There was a lot of speculation regarding the pandemic, if maybe people try to get research data from that. And we still don't know exactly what the motives of these attacks were, but since we were one of the affected institutions, I can tell you what we found on our systems. So at TU Dresden, we have a supercomputer cluster that's called Taurus. And it's mainly used for research inside the university, but also by a lot of researchers from all over the globe. And the cluster itself is quite normal, I think. You guys are more experts in this area than I am, so I'm just security guy. And the whole HPC area was new for me as well and for our team. So because we're focused with security in all aspects on the campus, and this is just a small part of it. So this cluster, the Taurus cluster, has a few login nodes. It had some export nodes, and there's this huge array of compute nodes, of course. All of these use some common network storage, which was NFS in our case. And there are, of course, a few administrative systems on the side there. And access to this cluster is, as usual, granted with SSH. So people log in on the login nodes with SSH. They can then schedule their jobs there and use the export nodes to import or export data for the actual computation. So initially, back in May 2020, we got a note or an email from the head of our HPC cluster team who said that they got a hint from another HPC cluster, which were friends of them, and they found an incident, that some IOCs, something wasn't right on their systems, and they just told our head of our cluster, these are the IOCs we found, this is strange, please look into your cluster as well. And this here is how this looked like. So they told us on their cluster, at the friendly institution, there were two binaries in etc fonts, which is a configuration directory regarding fonts. And one of those two binaries had this SUID bit set, which we just talked about earlier. On our clusters, they did a quick scan and looked on all machines for exactly this, and they found it on quite a few of them as well. So as you can easily see here, there is .fonts and .low, which shouldn't be there. Apparently last modified in 2017, which would mean this is here for quite a long time already. And also the S-bit is set here on one of these two files, which is highly suspicious. So this shouldn't be there, and it's also not part of any packet on that system. When we looked closer at one of these systems where this was found, we could also see, in this case with debugfs, this is a command which essentially looks at file system metadata to figure out more about a particular inode, that the file wasn't really there in 2017. That's just fake. The recreation time of this file was at the end of 2019, so at the 11th of December in 2019. This was also consistent with all of our other findings and was a very important date because we had to look at logs and we had to know something at what logs we should look at, because otherwise it's just too much. It's also for attackers much harder to modify this creation time than to modify the modification time. This can easily be changed with normal Unix tools. And this is exactly what happened here. So this 2017, the LS output just isn't trustworthy in that case. So we then went on and created the timeline and list of all compromised systems on this cluster. And as you can see here, we took the timestamps of these files when they were created and got this nice little timeline, which also was very useful in following the attack and trying to follow the attackers throughout the clusters. You see here, the very first earliest host we could find, which was most likely compromised, was the compute node we called here comp1. And it's also the only compute node which was really compromised in the end. We then figured out that they went next on to the login nodes, and afterwards, after quite a few hours, roughly 4 hours had to pass, they also gained access to all the administrative systems, which was the worst case, and in this, at this point our cluster was compromised. We figured also out that the checksums of the binaries we found there were essentially families of those. The binaries were, from functionality-wise, the same, but they were different families with the same checksum, which was interesting. And in the end, we did knew why, but it's not important for the actual case. Just had it on this table here. Okay. So looking at the binaries, we had two of them. First one was .fonts. It's the one with the S-bit set. And there was just a backdoor, so you can put that into Ghidra or any other decompiler or reverse engineering tool. And it's a very small binary which just launches bin bash, and that's it. And the interesting thing here is the S-bit in this case. So any user who has access to the system and can execute it due to the SUID bit will execute bin bash as root and has a root shell. So this is just a very simple backdoor, and yeah, nothing more to say about it. The second one, .low, was also executable, but didn't have a S-bit set. And this is a small log wiper. At this point where we investigated what this binary does, there were also reports from other sites. So in general, while we were investigating, there were also a lot of other institutions who had essentially the same problems and the same attack, and there was a lot of sharing and talking about and sharing of incidents and results essentially. So we knew these things already. So this log wiper just goes through a lot of log files and tries to remove traces from user sessions. On the last line here, you can see a sample invocation of this. So you just pass it a username and a host name, and then it walks through various log files and try to remove all traces from that. Okay. Now, regarding the actual forensic process, we first had to define a few questions what we wanted to figure out. First one was, okay, we knew one of the compute nodes was attacked first, but we didn't know how, so we needed to know what was the actual attack vector to place a binary there as root, essentially, on this compute node. Second one was then, how did the lateral movement to the other host take place? So next one was the login nodes. How did they gain root access there? And the last one was, of course, how did they then get 4 hours after that access to all the administrative systems? The procedure we used here was very standard, I would think. We just collected all the disk images of all the affected systems, which were needed a lot of space, and also we took weeks to walk through all that data. And we also took memory dumps of a few hosts which hadn't been shut down since 2019. So not a lot of hosts were in that state, but those that were, we just for safety took some memory dumps prior to shutting them down. Of course, during this whole process, the cluster was disconnected from the internet, which also caused all this media outrage where people were asking, hey, all these clusters are down. It's not just us, it's a lot of other institutions as well. But all of them were just doing their forensics in this time frame. Next, we looked at this data. So we created MAC timelines, which essentially uses the modified access creation and so on timestamps of all the files, and creates a timeline of when each file was accessed, which can be very helpful if you're looking, if you have a date, for, in our case, 11th of December, so we knew where to look in that timeline, what other files were modified at that day, for example. And we also did a lot of carving, which has proven to be very helpful. Carving is essentially looking at the unallocated disk space in a disk partition. So when you delete a file, normally, depending on what system you use and what file systems, just the reference to the file will be deleted, but not the actual data. And this is very useful for forensics and not good for privacy. On the other hand, that we can still try to recover old files, log files, and all other stuff that might help here. And this was also what helped us explain what happened in the end. We then wrote a few scripts to pass through all the data and search for known IOCs we got from other institutions which figured out stuff, and also to get log fragments which weren't on the file system anymore, so on the normal file system. Because when we started our investigation, December 11 was months away, and normally we just keep logs for a few weeks. So all of these logs were officially gone. At this point, we also didn't have a central log server. There were a few systems which logged to a central log server, and now the new cluster does that for all the systems, because this incident has shown centralized logging is very useful. But we had to restore our logs from lost fragments in the file system. We also looked at the timelines, of course, and did some memory analysis, especially on this compute node, which was compromised first, but we didn't find anything there, so memory analysis didn't help in this case. Okay, so going to the results. This is again our cluster. I just put a few names in there. So here are our 2 compute nodes, in fact, because the attacker tried to attack another compute node as well, which I used as comp2 here. And the other nodes are the same, as I already said. And the first thing we found, the most interesting thing, because we first looked at this compute node, was we are carving in unallocated disk space. We found some log fragments, and we could also verify that these log fragments were the real ones, they were true, because this particular system was also using a centralized log server from some research project, and on there we found the exact same logs. And there we could see that a few minutes prior to the backdoor being created there, if you think again, we had this creation time figured out earlier, you can see there was a user logged in. And this user was a legit user, one of our normal HPC users, and he had run a job there on this compute node and a few others. And then he logged in on the node. And during that login, this error message here occurred. So some bits stop being page shift, blah, blah, blah. Some kernel message error, which isn't very helpful when looking at this. And at the time, Google wasn't also very helpful what this error message means. I think today you find more references to this particular incident. And we also found that when the user logged out a bit later, session closed here via SSH, an error, which just an error, syslogin perform logout returned an error. This is all we had at this point, and these were the strings essentially we were trying to work with to figure out more what could have happened in that time. So between this error message up here and the second one, the binary was created. So there clearly was something wrong with this user logging in there. We then used carving to look for fragments, especially with these strings we found there, this pit page map and shift and so on. And we actually found 2 ELF binaries, which could be fully recovered from the var partition in the unallocated disk space again. And one of them had this string in it, CVE 2018 exploit, which most likely shouldn't be there if you're just doing your research there, if it's not security research at least. And if we look at this exploit, CVE 2018-9568 is essentially an exploit that targets a bug in the Linux kernel in the network subsystem, and which, as it says here, could lead to local escalation of privileges with no additional execution privileges needed. User interaction is not needed. So this was a working exploit for this particular issue. And as we then figured out, the kernel that this compute node was running at this time was actually vulnerable to this. The usually rather slow patch cycles in HPC systems, because everything has to be approved by vendors and proprietary kernel modules and so on, have the effect that security updates come late. And this was a case where an update would have helped. In fact, only one day after the incident on this host, an automatic update update was running, and it patched the kernel with a version which wouldn't have been vulnerable to this. Bad luck. We could also verify that the exploit payload creates actually this backdoor file. So this .fonts small binary was created as part of the payload and could then be used by the users. And we also figured out by verifying that this exploit actually works, so we can use that in a VM to check it works, that SMAP, which is Supervisor Mode Access Prevention, is a CPU feature, a hardware feature that does some sort of memory protection. I won't go into details, but this feature wasn't available on this hardware. So again, the generation after that would have been not vulnerable because it had this SMAP feature built in. So our CPUs were, I think, Intel Haswell generation, and the next one, the Prodwell or something like that, wasn't vulnerable anymore. So again, bad luck. By the way, we also knew from other institutions the attacker didn't just have this single exploit with them. So not all of the other clusters were attacked by exactly this, but they had a bunch of exploits with them, which they just used depending on the systems they were encountering. This also wasn't a 0-day at this point in time. It was well known because it says in the CVE it's 2018, so it was quite a bit older. So at this point, we pretty much know what happened. Alleged user was logged in, and his credentials essentially were used to log into one of those compute nodes, perform that exploit, and gain root access there, place the binaries there, and wipe the logs. We also have comp2, which is another compute node where we also know that the attacker logged in there, executed the exploit, and the node hang. So the exploit is not too reliable. It can happen that this machine just stops and you have a kernel panic, and after a while this thing rebooted and was working normally, and then there was no activity anymore because the attacker already had another host they could use in this comp1 case here. Next up is the lateral movement. Next question, how did they access the login nodes? Because these were next just a couple of minutes afterwards. And from the login nodes, we knew that the attackers already had a valid login because they were able to use SSH to jump over the login nodes to the compute nodes, though they were normal users there. But of course, we checked first for the kernel exploit there again, but we didn't find any signs that the exploit was used there as well. What we instead found was that here NFS was abused to misconfiguration issues. So back then we changed that for the new cluster. The NFS was mounted without no SUID and no exec flags, which essentially allowed the attackers to take the backdoor from the compute node, and on the compute node use the shared storage to copy that backdoor somewhere on that NFS storage. And the SUID bit was kept at that point. And then, yeah, they could just log into NoDev. I see in the chat here, NoDev is also one of those things you should set. Yeah, and then the attackers were able to log into the login node, which has the same NFS mounts, and just copy over their SUID bit backdoor over to that system and execute it there. And they are root on the login node as well. So this is really simple once you spotted that issue. And this is what the attackers did. So they used the shared storage here, and now we're also root on those 4 login nodes. Of course, this shouldn't have led to more exploitation, except the hosts where the user could log in normally, because there should be some separation between administrative nodes and normal nodes. But back then, this cluster layout still had a very flat hierarchy. It was possible to contact all the admin nodes. There were no real network separation. And it took them a few hours. We looked at a lot of log files, and we saw in a lot of log files that they actively scanned the network, tried a lot of logins in different services at this point, and it took roughly 3 to 4 hours until they were able to gain access to the remaining nodes. And this just happened because credentials were somewhere stored on one of the login nodes, which could be abused to gain further access to the root node of this whole cluster, which here is called admin 0. And once you have full SSH access as root to this node, it was easy to gain access to all the other systems. So yeah, these credentials were most likely from some previous maintenance work and weren't removed. Also, again, if you use SSH keys, please put a passphrase on there. So even if someone finds that key, it's still useless as long as you don't have the passphrase. And afterwards, attackers, the challenge then left was to know the host names of the remaining systems they could log into, but that didn't matter anymore. So all of these, and now they had a lot of systems they could abuse. Was a full shell history log of the attackers. So it was from any on anymore because they already had root access, but it was so interesting to see what exactly as soon as the attacker logged in there. And logs is that shell history logging was turned on some of these. This is not the most advanced form of logging. It's essentially just a bash feature which or etc profile to put a trap statement in there, and then on each command the root shell executed on that system, the command that was executed there, and the log wiper the attackers used and didn't automatically remove these log lines. So we're just lucky that we could find these. But again, we had to find that via carving because it was just too old. Normal syslog had already rotated out all these files. So the actual shell sessions looked very similar on the different nodes where we found it, but there were differences. So we are pretty sure that this is a mixture of manually typed commands and commands maybe copied from some kind of document and executed. You can also verify that by looking at the timestamps. So looking at the concrete example on admin 2 here, for example, 5 minutes prior to the backdoor being placed there in etc fonts, we see there is an SSH session as root coming in, and then stuff is executed. So the first thing they did here was trying to modify the environment, changing some settings to essentially not log something. So they're trying to set hist file to def null, for example, which didn't work against this particular form of logging that was used here because it's rather unusual and was handwritten in this case. And afterwards, they went on to gather some basic system information, IP tables, roots, host name, disk stuff, and then there was this long command which is just used to put a lot of configuration files, etc passvd, shadow, and so on into an archive and pack that up. They then had a similar command which was trying to find SSH credentials and other credentials, shell history logs, and so on, put that in another file, in another archive, and afterwards the attacker pinged an external address, a public address on the internet, and then used SCP to copy all of that stuff over to this other host. This particular address, also put a link in there, was known at this point in relation to this incident. And it belongs to the University of Shanghai in China, but this doesn't mean anything. So we didn't do some investigation. There were already the federal BKA, LKA, and so on that case, and we just told them we found that, and they went with it. I don't know what was behind that IP. And that's it. Then the data was gone, and the last thing the attackers did on this system was to clean some stuff up. They first, of course, had to deploy a backdoor there again, so they used SCP to just copy over the backdoor from other infected systems in and put it into etc, and afterwards executed the log wiper. So you here see again an example of how this log wiper is executed. And that's it. They then left the system and went on to the next one. So to finish, the attackers abused captured login credentials from real HPC users. To this day, I don't know exactly how they got these. It's very hard to follow that. So the user, which was alleged user on our system, which essentially caused this, was a normal user here in Dresden. So we could talk to him, but he didn't know of anything, and maybe he lost his key. And one of the The reveals or the follow-ups for this incident, also for a lot of other institutions, was to instruct people to not use a single, not even with a passphrase secured SSH key to access all the systems. So a lot of users were doing that. They had their single key and were using that to access different HPC systems at different sites, which were all publicly reachable on the internet, or at least some of them. And then it's very easy for an attacker to do phishing or whatever and just abuse these credentials. And so there has a lot has happened since then in the HPC community, specifically regarding two-factor authentication, also for SSH. So I have to drink something. So we also know that the attackers used exploits and some weaknesses specifically tailored to these target systems. So we had this particular CVE, but we know from others that they had different CVEs used. So they had a tool bag with stuff they could use to gain root on the systems. As far as I know, there were no cases of 0 days used here. So it's all just known exploits with IOC, with proof of concept code from GitHub and so on. And still, this is a prime example of an APT, advanced persistent threat, since this lateral movement through the network and deploying backdoors everywhere is quite common for these type of attacks. Positive things, once we knew the IOCs and the affected systems, we could quickly discover what other systems we had to look at and to verify if other systems were affected, and then shut all of that down, or at least break the internet connection there and do our investigation. We found no further indications that this access was abused to do anything. We know from others that this was the case for most of them as well. So the attackers just placed backdoors there, but didn't use it for anything, at least not yet. There was one case they reported they had crypto miners running, which might be quite effective on an HPC system. But still, some people said that this was a different incident. So I can't say for sure. I can only say for us at least, we didn't find any sign that this was ever abused. So the resulting damage from all of this was mostly the cluster was down and we had to reset up everything. But this had also the positive sides that we could rethink, or our HPC guys, in fact, I didn't do that, could rethink the cluster layout and implement additional security barriers, do network separation, centralized logging, SSH with two-factor authentication and so on. And this is something I would say in general, this is a positive thing of this whole incident. The HPC community seems to be more aware now of the potential downsides of some decisions. Yeah, and if you're interested in a bit more detailed analysis, I wrote this blog post here, which has a lot of the stuff I just told you, and maybe a little bit more, so feel free to read it. Yeah, and with that, I'm open to questions.
Yeah, thank you. That was really interesting. Yeah, whoever has a question can just write in the chat or say something.
I have to say, again, I'm not an HPC expert. So if you ask specific questions to HPC, I probably don't have an answer. We should read the questions out loud. And did I understand correctly that the main damage was the downtime and installed backdoors? They copied something over to their server, but that was nothing sensitive. Yes. So the stuff they copied, there were just, of course, there were usernames in there, which were not full names in this case, but short names we use internally. And there were shadow files with passwords. And we, of course, advised them to reset all the passwords. So also the credentials of all HPC users were reset. The keys were no longer valid. So all of that had to be recreated. But apart from that, the systems didn't contain any sensitive data. So luckily, that was it. What do you mean by efficient scraping?
Yeah, you should probably do not PXE boot and reinstall your node, but to protect your deleted data, I guess. Or what do you mean, Sven?
I'm also not quite sure.
But he's asking, when you do PXE reinstallation, what would be efficient to prevent the reinstallation, that it overwrites the deleted data to do the forensic.
Oh, okay. That would be very pro-forensic. Usually the question goes in the direction of, oh, we can recover stuff from the file system. We don't want that. How can we prevent that? If you actively want that, I assume the normal file systems, X4, I think was used here. It just deletes references, so you could just use it normally and don't set up security features if you want this forensic this way to do forensics, not hinder that. I don't know what he means by efficient scraping. I'm not sure we got the question here.
Can you hear me now?
Yes.
Okay, so efficient scraping. Occasionally I have to reinstall a compute node, and in order to allow scraping in case of an attack, I would like to avoid that the scraping also reveals remnants of prior installations of the system. So basically a DD def0 of the entire hard disk should be maybe done doing Anaconda to allow that any data that is found doing scraping in case of a successful attack does not reveal anything that's not helpful because it involved the other system before it got reinstalled.
So you want a clean system full of zeros, essentially.
Yeah.
Okay.
Like sdelete on the sysinternals on Windows, or a DD from def0 to everything.
Yeah, that would have been my my recommendation there. You can just use DD to override it zeros, right? Oh,
okay.
What would be, that was what I would do.
I mean, on the newer SSD versions, not on every SSDs. If you have these in compute nodes, you can do a secure erase. That is much more much faster.
Yeah,
that's the only thing I would think of, which might be more efficient. But yeah,
probably doesn't wear down the solid state disk as much, I think.
From what I know is that it is really a secure erase. So they internally erase every flash parts simultaneously with zeros. But yeah.
But I don't know how to integrate that into Anaconda PXE stuff, so I'm not familiar with that. But if it's possible to execute custom commands during reset up, just include that as a command there. Okay. SSDs with secure erase, they change an encryption key. That makes sense. Then it's of course very fast. Are there any other questions? Doesn't look like it, which is fine.
Yeah. Okay, Pascal. Thank you again. That was really nice.
Yeah. Thank you.
Really helpful.